Mathematical induction. So induction this is your reasoning skills, like you reason out when you use induction here. And we're not going to actually do the proofs, but I want to show you this because this is where these summation formulas came from that you're going to need to memorize. And so the proposition is true for all natural numbers if P of 1 is true, and then P of K plus 1 is true. And so what they're just saying is that in order for these induction theories or these mathematical induction to work, then it has to be true for your first term, and then it has to be true for every other term after that. That's basically what it's saying here. All right. And so if you flip to page 478, you start to see some of these summations that were based off of the patterns that were formulated from mathematical induction. All right. The first thing is that if you have summations, so that little Greek symbol right there means add it up. We've done that, right? You can multiply the entire thing by something, and that's fine. You can add summations. So if you have two different summations, you can add them. So you can go from one number to a number in between and then start there and go to the end. And that's going to give you the same thing. These are just kind of rules of summations, that you can add summations or you can multiply an entire summation by an answer. That works as well. And so the ones that we're going to memorize are these partial sums right here. The first one is if you're adding up something that is just one term, and K represents kind of your variable in it, then you can get that summation formula from the n plus 1 over 2. This should look familiar, all right? This is when you add up consecutive integers. So if you have 1 plus 2 plus 3 plus 4, this is the little Gauss's theorem. This is however many you're adding up times the next one divided by 2. All right, and so that is the summation formula for just one. If you are squaring it, so let's say you're taking 1 squared plus 2 squared plus 3 squared plus 4 squared, all right? Then you can replace that with your top number. So just like with adding 1 to 100, you could say I'm going to take 100 times 101 over 2, and that will give me 1 to 100. If this was squaring them, 1 squared plus 2 squared plus 3 squared all the way up to a certain number, you can take that last number and just plug it in. And that will represent what happens if you were to square every number from 1 to that number. Cubing, if you were to cube it, then instead of adding up 1 cubed plus 2 cubed plus 3 cubed and so on and so forth, then you can just take the final number that you're getting to and plug it in. Let's say you wanted to add all your cubes from 1 to 10. You would just take a 10 and plug it in. 10 squared plus 11 squared over 4. And that will give you 1 squared plus 2 squared plus 3 squared all the way up to 10 squared. All right. It'll give you all the way up to cubed. It'll give you all the way up using fourths. So these represent what happens when you add consecutive integers or when you add consecutive squares, cubes, and then to the fourth power. That's what these represent. And so you can very quickly get to the summation as opposed to plugging in a 1, squaring it, and adding a 2, squaring it, adding a 3, and doing it that way. This is how you get to the summation without having to add every one in between. It's a shortcut. All right, so let's look at using these. All right, it wants to evaluate these particular things. All right, now, when you have a constant, and they actually didn't give us the constant, they gave it in the partial. So when you have just a constant, that's going to be multiplied by n. When you have a k squared, you're going to look to that formula and you're going to replace the k squared with the shortcut for k squared. So if I were to rewrite this, there's a couple things you could do to figure out the sum. The first thing is you could plug in a 1, plus plug in a 2, plus plug in a 3, and go all the way to 17. That's gross. We don't want to do that, okay? So what we're going to do is we're going to replace it with our shortcuts. We're going to say 4, and instead of k squared, we're going to plug in our formula for k squared, all right? We're going to say, well, that's n plus 1, 2n plus 1 over 6. That is my shortcut for k squared, okay? And then for 9, any constant, you just end up multiplying by how many times? Because you're literally saying 9 plus 9 plus 9 plus 9 plus 9, 17 times. There's another way to write that. That's 9 times 17, okay? And so now all of a sudden, I don't have to add up each one. I can say this is what it's going to actually do, and I'm just going to plug a 17 in, and I'm going to figure it out that way. All right. Now there's going to come a time, and this is later on in our calculus world, where we do limit theory, and you have to actually simplify these before you plug anything in. Okay. But for this, you don't have to do limit theory. You don't have to simplify them. You can literally, at this very point, plug in a 17. Plug in your n. Your n is 17. I'm getting that from how many times I'm doing it, okay? And so I can just say, well, that's going to be 4. 17 plus 17 plus 1, that's going to be 18. 2 times 17 plus 1, that's going to be, what, 35, right? Over 6 minus 9 times 17. Again, you're going to want to use a calculator because I don't want to do all of that by hand. But that is going to give you what happens if I were to say 4, 1 squared minus 9. Plus 4, 2 squared minus 9. Plus 4, 3. You see the pattern here, right? This, way longer than memorizing that, okay? And it's going to give you the same number. So when you plug it all in, you're going to get a ginormous, 6,987. And I actually feel like it would be more than that, but that's what it is. All right, so that's what you're going to do with these. That's why you want to memorize those summations, because you can use them. All right, let's look at the cubed one. This is just k cubed. All right, this is just k cubed. Here's the thing. They want 8 to 20. All right, so my formulas always start at 1. This is vitally important. They always start at 1, which means when I do the summation formula, it's going to give me what happens from 1. So when I replace this guy with n squared, n plus 1 squared over 4, that's actually the summation from 1 to 20. What do I not need? I don't need 1 to 7. So I have to subtract the summation from 1 to 7. So in this one, I'm going to have to say, well, I also need to do this guy. So this one, I'm going to plug in a 20 for all of these n's, right? But I need to do the summation, same thing, because it's the same, it's k cubed, right? But now, for this one, I need to plug in a 7 and subtract him out. Okay, so when it starts at a number other than 1, keep in mind your summation formulas are all from 1 to the top. So you have to potentially use it twice to get rid of what you don't need if it started at a different number than 1. Summations individually and just subtract. That's why those properties are important, because you're going to want to say, well, I'm going to take this guy here and I'm going to subtract this one here. And then that's going to give me my overall total of from 8 to 20 instead of 1 to 20. All right.